Hey students, I thought I'd make a couple of extra little examples here. Number 28 and 23 come to my mind because I like to do, let's see, example 3, or 1, 3, 10, 28, 29, 23, 55, and 59. That's on my list of examples I'd like to do in class, and we just kind of ran out of time. But I did notice that 1, 3, 10, 29, and 55 I did in the lecture videos. So you can see those worked out. And also 59 makes not only a good example, but it's also a homework assignment. And so I've made a video solution for that. And the two that are missing then from my list is 28 and 23. And so I thought I would just make a video here of those two examples. And then you would have the whole list and you can watch as many or as few as you need to kind of absorb this material here. So let's start with number 28 and do them in that order because I printed up number 28. And it's a black rated problem, so it should be relatively straightforward, whereas 23 would be a little more advanced. And it has some nice engineering and technology we need to talk about before you can even do this. And so I really feel like I need to talk a lot about 23. But starting here with number 28, it says, imagine a wire with a linear mass density of 2.40 grams per meter, and it's encircling the Earth as it in its magnetic equator. Where the field model has this value, it's horizontally north. That's important. What is the magnitude and the direction of the current that will keep the wire levitated immediately above the ground? Okay, now to fully understand this, we have to kind of understand that we have the Earth, and it's rotating around what we call the geographical North Pole. And then there is this core, and the core is actually an inner and an outer core, but the outer core is a liquid, and so as the Earth spins, the molten nickel and iron make currents, and the currents make a magnetic field. And so it's sort of as if there's a bar magnet buried inside the Earth. And so it makes this magnetic field. And not so much relevant for this problem, but notice I drew the bar magnet at a slight angle from the rotational axis. And in fact, your author actually has a better picture. Maybe I should grab that picture. Here's your author's picture, and he does a good job of saying, okay, here's the Earth, here's the rotational axis, so we would call the geographical North Pole, and then the magnetic pole is tilted about 11 degrees from that, but perpendicular to the magnetic pole is the magnetic equator, not to be confused with the geographical equator, again, a 11-degree tilt. But what's going to be real important and relevant in this problem, although maybe not too much, because they make it very clear that the field is horizontal and north. And that's what I want you to see in this picture, that along the magnetic equator here, the field goes straight north, straight up. Because, of course, to get a force on a wire with a current, we need to know the direction of the current as well as the direction of the magnetic field. And that's what this first step is. And so before we can jump into the numbers and do any of the calculations, we need to realize that we're going to be wrapping a wire all the way around the Earth at its magnetic equator. I guess if I maybe grab this as the wire wrapping around the Earth, and maybe grab one of my souvenir balls here and say, okay, if I wrap it around the Earth, you can see then that the current is either going to go from the west to the east or the east to the west. And since we're right at the equator, we're trying to get it so that it, lifts the wire up and levitates it, because we know gravity is going to be pulling the wire down. And so we want the magnetic force to be up, away from the earth, while gravity pulls it down. And if we can get those two equal, then it would levitate. And that's the conceptual argument here in this part here, where it says, what is the magnitude and the direction of the current? And so we learned in class that the force on a wire that is carrying a current in a magnetic field is actually the solution to this integral. But even easier than that, and I'm sure that's why the author labels it as a black problem, is that if the magnetic field, the current, and the angle don't change, then we can factor out all these factors outside of the integral. They're all constants. The angle's a constant, the magnetic field is a constant, and the current is a constant. And we end up with the easy special case of just L cross B. And that's what we'll use in this problem then, to figure out both the magnitude and the direction of the current in order to create the appropriate force. Now, why don't I start with direction? So I come back here and my ball and say, okay, so here is the current. And if I call to the top of the screen the north and bottom of the screen the south, then if the current goes west to east or east to west, maybe I'll do east to west first, and I do this cross product, I'd put my fingers in the direction of the current, rotate my hand so that I can close towards the magnetic field. And notice my thumb is down, so that would make the wire get pushed into the earth magnetically. Exactly the opposite of what we want. So that's not good. So we don't want the current going from the east to the west. But what about the other way? What about from the west to the east? And in that case, I'd take my right hand and put it in the direction of the current, close my fingers towards the magnetic field, which is towards the north. And you can see then my thumb points outward or towards the screen, which is then lifting it upward here, something like that. And that's what we would want for our fields here. Okay. So with that in mind, I guess I've answered the first part, that we want the current to flow from the west to the east. And then when it comes to the strength of it, well, we would want the magnetic force to equal the gravitational force. And then taking the cross product and setting it equal to the gravitational force. And then here's where that direction comes into play. Of course, we already stated that it's going to be a constant angle. But again, if this is wrapped around the globe here, as the current goes from west to east, kind of along this arc here, and the field is always going towards the north, this is always going to be 90 degrees. And so we have an ILB equals mg. And now to get the current by itself, I'll bring the L and B to the other side, and I'll even group this together, because this right here is the mass per length. And that's what's given in the problem. They don't give us the length, although we could look up the radius of the Earth and figure out what the length of around the equator of the Earth is. And then use this to get the mass. But it's probably easier just to group it together and call it mass per length. So this number here, changing the units to kilograms per meter, this is the 2.4 grams per meter that's given right there in the problem. The G is the 9.8 meters per second squared, and the strength of the field is given as 28, what was it, 28 micro Tesla. And so grabbing a calculator somewhere here, let me put in those numbers. So 0.0024 times 9.8 divided by 28 micro, and I get 840. And this should come out to be amps, probably worth checking. Like here, I'll go kilogram over meter, and then I'll go meter per second squared for here. And this is that Tesla. And if you remember, our definition of a magnetic field was how much force do you get per charge moving at a unit speed. So that made the units come out to be newtons per coulomb per meter each second. So our Tesla here should be a kilogram over a coulomb meter per second. And so if I look at this carefully, the meter will cancel off. And if I group the kilogram and this meter and this per second together, that gives me a newton. And then that newton cancels with that newton, and I'm left with just coulombs per second, which is the amp. So yeah, it does work. 840 amps there for our first one. Okay, well, if that was helpful, which I hope it was, let's head off to the harder one. And number 23 says this: a picture tube in a TV uses a magnetic deflection coils rather than an electron deflection plate. Now, this is where I thought I better give maybe kind of a little mini lecture here on, how does this TV picture tube even work? And we talked a little bit about it in the class. It was also in the reading, but it's worth reviewing here. And it starts off this way, that you take usually tungsten, since it can handle the heat really well, and you hook up a battery, and we call this the filament part of it. We just run some electricity through here, and then this gets really hot. In fact, it gets so hot, the tungstens bump into each other, and they boil off electrons, is the phrase we like to say, because they hit so hard. And then not far from them is another plate that we call the accelerating plate. And we make it positive in nature, and we usually do that by hooking up another battery. And this pulls the electrons that boil off to the plate, and some of them, what I'll call the magical ones, head right towards a small little pinhole. And so this whole metal plate has a small hole, and so just enough, whatever enough is, I'll call it 1%, make it through this hole. The other ones all hit here. But the only ones we're going to be interested in is the ones that go through here. And of course, then they go racing through really, really fast. Because another part of this is somewhere over here is the screen. And usually this is designed so that if there's no deflection of this beam, it will hit the center. In fact, I think that even says that later on here in the problem. It says, let's see, the electron beam hits the center of the screen. It says when the field is turned off. Yeah, so with no deflecting of this beam, it goes straight through. And when it hits here, it would give off a little bit of light right in the center of the screen. But to make the image on the screen, then, we need to control this beam. And if you're looking at the front of a TV screen, then the beam would hit here, 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 and then go down a row, here, 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 here. And then go down a row, here, 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 here. And so it sweeps out across the screen. In fact, kind of an interesting subtlety. The old-fashioned ones would actually scan every other line and then come back and do the inter ones. And so they called this an interlace, just because of the flicker effect. Today, TVs use more of a progression, and they can just do every line. Everything goes so much faster and so much cleaner that you don't lose the flicker. They're actually LEDs most of the time anyways. So you have a progressive scan. That's why you have things like, 1080p for progressive scan versus the 1080i for interlace. I don't even know if you can find the interlace anymore. Anyways, but I digress with some old technology there. But the bottom line is we need to make this beam then hit different locations on the screen in order to give off the light. And of course, we can turn it on and off. And so it goes bright, dark, bright, dark. And so you get a bunch of pixels lighting up. And that's the technology of making a picture tube. And so that's kind of what this little mini lecture is all about. That, hey, we gotta have a little picture tube. How does this thing work? And so we deflect them, and this is where it says here, it is deflected with magnetics instead of electrical. Because you could control this beam electrically. And when we use an oscilloscope in class, that's what we'll do. We'll deflect the beam with an electric field. But this one says a picture tube in a TV uses magnetic deflection. And in fact, this is the final part of this. It uses some coils rather than an electron deflection. Suppose the electron beam has been accelerated by 50,000 volts. And so this part of the problem is saying right here, what voltage did we use to accelerate that? That conceptually needs to tell you that we know the speed of these electrons as they come racing out. And we'll do the math here on those in just a second here. But then it enters a region where there is a uniform magnetic field that is 1 centimeter wide. And so maybe right here, there is a region that is 1 centimeter wide and has a magnetic field. And it is this strength of the field that will bend this beam either down or up. And if I have let's see. I guess it depends which way the field is. So let's do this. And I'll do green. If I make the field going in, and as a side note, not shown here, to make that field, I'd have to have another battery and a coil here. Maybe it would look something like this. Maybe I'd have this crazy thing here. And so I would send some current through here. And depending on what direction the current is, I would get a field. And so once I have this field, I can then see which way it would deflect. Now, so in my picture, let's see, if I do a V cross B, let me set this up here. So here's V, here's B. So V cross B would be up. And if these are electrons, then the force would be down. So in my picture, as they enter here, they're going to make a part of a circle. And I don't know if I did a good job. All right, so not drawn real well, but that's supposed to be a circle that, has some radius. And I suppose that's another question we need to talk about. We did that in the lecture. What is the motion of a charged particle in a magnetic field? Well, once it exits, it continues on in a straight line. Okay, and so there's Newton's first law of motion, and it hits the screen. So if we had a weak field, it would only bend it a little bit, and it might hit right about here. And as we increase the field, it would hit further down. And that's how we would control where the beam is hitting on the screen. And we can control the strength of the field by how much current we run into these deflecting coils. And so that's kind of the logic here. Now, of course, the way I've drawn it, this is an up and down deflection. I say that because if I keep reading the problem, the screen is located 10 centimeters from the center. So 10 centimeters from the screen to the center of these coils. And the screen is 50 centimeters wide, and that means from the center on down is 25 centimeters. And then this is the part we read before. The electron beam hits the center of the screen. That's why I got the 25, because that was the half of the 50. What field magnitude is necessary to deflect the beam to the side of the screen? So all the way down. So all the way down, we got to deflect at 25. Now, they do say the side, so it might mean left or right. So if I was a viewer looking in from this side, I might need a field going down this way. But it looks better on my picture if you let me go and draw it up and down instead of in and out of the screen here. Okay. So again, that's our goal. What is the strength of that magnetic field? All right, so like I said, I wanted to do this problem for a couple reasons, and this was one of them. Just kind of talk about the engineering and the design between of a pitcher tube, or what we called a cathode ray tube. Although usually cathode ray tubes deflect it with an electric field, and pitcher tubes deflect it with a magnetic field. And so this is what we have here. And so that's why this needed a little mini lecture. In fact, in going on with this little mini lecture, when I put this equation that is the force on a moving charged particle in a magnetic field, this is where we go back to physics 121 and say, okay, from this logic, the force here must be perpendicular to the velocity. And when you have an object that's moving in a particular direction and you put a force perpendicular, and if it's always perpendicular, it always makes it turn. It makes it do an arc. And that was this argument, in case you had forgotten it from the lecture, that this has to be an arc. This has to be a piece of a circle. Okay? And then, of course, the other part of this, I'll call it mini review lecture, was that if something does go in a circle, then the force, which in this case is magnetic, has to equal to ma, and the a for a circular motion is the v squared over r. And so mv squared over r must equal the magnetic force. And the magnetic force is then qvb, and sine of 90 degrees equals to mv squared over r. So there's the magnetic force. And so when the electron is moving in the magnetic field, it has the magnetic force. And since that's making a arc of a circle, it must equal to mv squared over r. And then if we simplify this a little bit, sine of 90 is 1. I'll drop that. One of the velocities drop away. And if we solve this then for the magnetic field, we see here that if we know these 4 items, the mass, the velocity, the radius, and the charge of the electron, we can get what's being asked in this problem, which is what is the strength of the magnetic field. Now, since they're electrons, the mass and the charge is easy. The harder part is these two. What is the velocity and what is the radius? Now, we touched a little earlier on the velocity, so let's do that again. The velocity comes from this accelerating plate here. And so if we remember that the change in kinetic energy is equal to negative the change in potential, I guess that's from Physics 121. And then the change in potential would be Q delta V, which is what we get from the chapter 25. We could put this number in. So this is a minus, and the charge of the electron is negative 1.602 times 10 to the minus 19 coulombs. The change in potential is where that phrase, through a 50 kilovolt potential difference. And so this electron is going to go to an increase. That's why we hook the battery this way. Here's the longer bar plus. And so it is an increase of 50,000 volts, which I will write as a joule per coulomb. And so this first part, the 2 negatives I can get rid of. But then 1.602 times 10 to the negative 19 times 50, 1,000. And so we're looking at a change in kinetic energy of plus. That's good. That means it goes faster. 8.01 times 10 to the minus 15 joules of energy. And if we set that equal to the change in kinetic energy, which has another nice little part of our mini lecture here, is these electrons, when they boil off, are barely moving in retrospect to how fast they're going to be moving when they're put near such an extremely high potential. And so we'll just say that their starting speed is near zero or negligible, because again, they just heat up and they bounce around and they pop off, and they're barely moving at all. Especially when we do a little bit of math here and find out what this incredible speed is. And so this final speed is nearly the speed of light. It's, let's see, not quite that close, times 2, divided by 9.11 times 10 to the negative 31 for the mass. That should be the velocity squared. So if I take the square root of all that, we've got 1.33 times 10 to the 8th. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So this is incredibly fast. You might even argue too fast. Those of you who have been through Physics 123 know that when we start to get about 10% the speed of light, and this has got to be about 44% the speed of light, we have to start changing our mechanics a little bit. And that explains this last part. It says ignore relativistic corrections. And for 2 reasons. 1, we just make the problem a little bit easier. 2, not all of you have had chapter 39 yet, which is, in fact, the way the book's laid out, we're not even that far. So if you were taking the book in order, and which, like I said, those of you who haven't done 123, you probably don't even know what I'm talking about here in relativistic effects. And so we'll talk about that next May when we're working on relativity. But really, we should not be doing a problem with this much voltage without relativistic corrections, which by the way, might be a chance to answer, well, the author could have made a lower voltage, but he didn't. And I think so because this is more of what we see in real TVs. This is a real honest engineering value, which then means that the engineers designing this need to consider these harder and more complicated relativistic effects. That's a long way of saying that, you guys who are going in engineering and your mechanics, you need to do a lot more than Newton's mechanics at times. If you were an engineer and you ignored that, you would get terrible results. Probably be fired because this is just careless. Anyways, but for us, as we're kind of being educated and learning along here, we won't worry about that fact that this is greater than 10% of the speed of light. We'll just do the old Newtonian stuff we've learned at the beginning. We won't have to do any corrections. And so let's go from there. But that gives us the speed, which brings us back to the fact that, okay, so we've got the mass, the charge, and now the speed. The fourth thing we need is the radius. And the radius is kind of buried in all this geometry. And let's see if we can look at the geometry here, because we do have numbers like it's 10 over to here, it's 25 down to there, it goes in the arc of a circle. And so this is some kind of angle, I'll call it theta. And I can see here then that this theta, this r, and then this distance here, which is the 1 centimeter, are tied together. So in other words, sine of theta is this 1 centimeter over r. So if I'm looking for r, if I could somehow get theta with knowing that distance, I can get r. And that's good. Because this theta probably is connected to somehow how this thing bends here. And so let me draw kind of a straight line going back. This would be the line of the final velocity, and maybe I'll draw a line of where it was going without the magnetic field. So again, these two cross. In other words, this changes right here by some angle. Let me call it alpha. And alpha is going to be pretty easy to get because alpha is, this triangle right here. This is this 25 down and 10 over. So the inverse tangent of the 25 over 10 is the alpha. And I'm not sure if I'm going to need that, but I bet that is connected to this. And so I bet there's a direct connection. So if I find that, with a little geometry, I think I can get that. And then with a little trigonometry, I can get my r, and then I can finish the problem. So that's my strategy here. Why don't I come over here and I'll just go tangent of alpha is 25 over 10. So let's see, am I in degrees? Yes. Do I want to stay there? Sure, why not? So let me go inverse tangent of 25 over 10. And that's 68.2 degrees for my alpha. Okay, so maybe I'll put it here in my picture. And here's the kind of the last and magical step of the geometry here. If you look at this four-sided object, I don't know if the black will stand out from the blue much, but across here and down to the center of the arc, then across here and back, something like this. I see this four-sided object, and the angles inside of a four-sided object add up to 360. But this and this are tangents, so these are 90 each. And so that means this theta here, theta, plus this angle, let me call that gamma, plus gamma, have to equal 180. But you see also this gamma and my alpha, so my gamma plus my alpha, also have to be 180, because that's just a straight line. What do they call that? Adjacent angles add up to 180. And this is great, because if I, set these two equal to each other, and then the gammas on each side, is this going to say theta and alpha are the same? Okay, good. So not only is there a connection, it's an easy connection. They are the same. Okay, so now to finish off my trigonometry, and maybe I'll do it down here. Now I'll do it over here on the side here. But the trigonometry here says that the sine of theta is the 1 centimeter over the radius. I suppose I should be careful with my units. That's 1 divided by sine theta. And so that's 1 centimeter. So this is going to give me an answer in centimeters. But so 1 divided by the sine of that last answer is, we'll call it 1.08. And so 1.08 centimeters. All right, so now I have everything I need here. I can then put in the mass, 9.11 times 10 to the negative 31 kilograms. I can put in the speed that we did here using our conservation of energy. 1.33 times 10 to the 8th meters per second. I can put in our radius that we got through some geometry, and I will also convert it into meters. And so there's my meters. And then the charge is the 1.602 times 10 to the negative 19 coulombs. I suppose you might say the charge is negative, but remember back here, I did basically the magnitude of the force equals mv squared over r. I didn't really pay attention to direction. So right here, this is just ignoring all the negatives there. So I will ignore that. And so number-wise, I get what? So 9.11 times 10 to the negative 31 times 1.33 times 10 to the 8th, 0.0108, 1.602 times 10 to the negative 19. And we're looking at 0.070. And this should come out to be Tesla. Let's give it a try here. Let's see, this would be kilogram. This would be over meter. This would be meter per second. This would be coulomb. If we did this, let me put another second and then divide that by a second to make it balanced, because that right there is a Newton, and then Newton per coulomb per meter each second, and that's our definition of a Tesla. Good. So it does work. And then let me just make that then into a milli. And so 70 milliteslas is the final answer. So, like I said, a good problem, because it did have some tricky geometry, but, well, it had a lot of everything. And that's what I really liked. It really forced me to kind of do a little mini lecture on this whole idea of how these magnetic deflections work on a screen, and of course how they get their velocity. And so the whole electron gun, the magnetic deflection, and so all the engineering that goes on here is needed to understand this problem. And so it's a good explanation of the CRT, but it also does a lot of physics 121 stuff, the circular motion, the conservation of energy again. It does some geometry. And of course, the big thing for this chapter is it does the magnetic force on a moving charge in a magnetic field. All right, well, hopefully that was helpful, and take care. Bye now.